So now we've covered lots of important fundamentals. We can pick out some key single qubit gates that are going to be very useful and come up again and again as you work with quantum circuits. So I will call this slide single qubit gates. And I think I'll have a go at doing this by doing lots of individual block spheres showing the effect of each gate. So the first one we're going to think about is basically the only gate that you can do on classical bits, which is the NOT gate. So, I mean, the reason that quantum bits are a lot more exciting than classical ones is with classical ones, you can flip 0 to 1 and 1 to 0, but you can't do much else on a single bit. Whereas with quantum bits, you can rotate everywhere in between. But we can also do everything we can do on classical bits. So let's start with that, the NOT gate. So if we have our block sphere with 0 and 1, what the NOT gate does is rotate. Actually, I should draw this. It rotates 180 degrees about the x-axis. And that's why we actually write it as an x. And we use this hat to emphasize that we're writing down an operator. So you might see me use this hat sometimes, but sometimes I won't. So the x acting on 0 sends it to 1, and x acting on 1 sends it to 0. And so that's this way around. And as a matrix, we can write it as 0, 1, 1, 0. And you can check for yourself that this is unitary. And that's the NOT gate. And you can also have a go at finding the eigenvectors and eigenvalues of this matrix. And what you'll find is that the eigenvectors are the plus and minus states, and you can see this from the block sphere, that if you do an 180-degree rotation about 2 points on the x-axis, then nothing's going to happen to them. And so we can, let's go through this, because there'll actually be an interesting point that will come out here to do with phase, which we've not mentioned yet. So I'll go through this. So if we apply x to plus, then this is applying x to 1 over root 2, 0 plus 1. And what I said before is that we can kind of multiply this x through. And so that will flip both of them. And so then we'll have 1 plus 0, which is the same as plus. So we can see that plus is an eigenvector of x with eigenvalue plus 1. And x acting on minus will give 0. Well, we'd have x acting on 0 minus 1. So when we flip these, we get minus 1 over root 2, 0 minus 1. And so that's minus minus. So we have the eigenvector minus with eigenvalue minus 1. And what is interesting to note here is that even though when we have the point on the x-axis, on the minus side, when we do an 180-degree rotation, it doesn't change. We do actually introduce this phase. So we call this the phase. So the minus sign, that's the phase of -1. So we have introduced a global, we call it a global phase because it's a factor that multiplies the entire state. And important things to note about the global phase is that it doesn't affect measurement outcomes, because it's when we take the modulus squared of the minus state, it's not going to affect the measurement outcome. And in general, if we have a state psi and we times it by -1 or times it by I, then when we take the mod square of the ket as a whole, or of any coefficients of elements of it, if we write it out in terms of something else, then the overall minus sign, or I, or whatever factor it is, won't affect the measurement outcomes. However, this phase is important if it appears when we are acting on a minus state that's being added to something else. For example, you need to be careful not to think, oh, X gets this global phase out on the minus, but it doesn't actually matter, because it does matter if you're trying to apply X to a combination of plus and minus, because then when you apply it, you'll get 1/√2 plus minus minus, and this is a measurable outcome. It's a measurable difference, because this state actually corresponds to 0 and this corresponds to 1. And so the phase that's been introduced here, we call a relative phase, and this does affect measurement outcomes. However, you can see that the global phase is something that we can't see on the block sphere. It doesn't, that information isn't there, and it also doesn't affect the measurement outcomes. So that's the X gate, and we can similarly define Y and Z gates. So the Y and Z gates are defined similarly. So Y is 180-degree rotation about Y axis, and Z is 180-degree rotation about Z. And the matrices for these are 0, I, 0, minus I, 0, and 1, 0, 0, -1. And finding the eigenvectors and eigenvalues of those is a useful exercise, but what you'll find is the eigenvalues are all plus or minus 1 for all of them, and you can find the eigenvectors as well. And I think it might be useful to comment at this point that the eigenvalues of unitary matrices will, in general, can be written in the form e to the I phi. They always have to have modulus 1. And you can see this if we have a unitary matrix which has some eigenvalue A, and then we apply then we know that if we take the dagger of this, then we get psi u dagger, and that's going to be equal to psi a conjugate. And if we take the inner product of these two, then we have this equation. So we have a star psi, which is mod a squared. And this is identity. So mod a squared has to be equal to 1. And so that means that that a has to be, in general, in this form of e to the I phi to have modulus 1. So that's a general result for the eigenvalues of unitary matrices. Right, so now we have our basic single qubit gates x, y, and z, but so far we can see that x can flip us from 0 to 1 and 1 to 0, and you'll see with y and z that they can also flip us from a state on one side of the sphere to the other. So z can flip us from plus to minus and minus to plus. But we want to be able to do more interesting things like creating superpositions of states, or changing from something in a superposition to something that's not in a superposition. So for that, we're going to introduce an exciting gate called the Hadamard gate. So this is our first gate that lets us create superpositions in a basis where we didn't have a superposition before. So with our, try and do a better circle, with our block sphere, if we have our z and x axes, then what the Hadamard gate does is do, again, we can think of it as an 180-degree rotation, but about the axis that's halfway between x and z. So about this, about this axis here. So we do a rotation from 0 to plus and plus to 0. So h applied to 0 is plus, h applied to plus is 0, and likewise we can have the minus and 1 states, and if we have the state 1, then it will be rotated to a minus, and minus will be rotated to a 1. So h minus is 1 and h1 is minus. And the matrix for this gate is 1, 1, 1, minus 1 with a 1 over root 2. So you can use this matrix to check all of these statements here. And something which you can see here that's also true for the x, y, and z gates is that they all reverse themselves. So they're all their own inverse. And so just applying 2 of them to any state is the same as applying the identity to that state. So that's the Hadamard gate. And now we'll look at another gate which will be coming up again and again. This is kind of a general gate, you could call it. And this is the phase gate. And the general form of the phase gate is 1, 0, 0, e to the I phi as a matrix. So I'm going to create something that I'm going to call the phase gate family tree. This isn't official terminology, it's just me. So let's see what happens. This line is the value of phi, and we're going to see what happens when we let phi take a few different values. And these are going to be 0, pi on either end, pi minus pi. We're also going to have pi by 2 minus pi by 2, and pi by 4 and minus pi by 4. So let's see what happens with this family tree. When we have 0, we have 1, 0, 0, 1, which is the identity. When we have pi, we have 1, 0, 0, minus 1, which is the Z gate, and the same when we have minus pi. When we have pi by 2, we have 1, 0, 0, e to the I pi by 2, which we call the S gate, and e to the I by pi by 2 is just I, so we can replace this with I. And e to the I minus pi by 2 is minus I, and this is the S dagger. So we can see that for the first time in our single qubit gates, we have a gate where the dagger is not the same as the inverse, and so S does not invert itself. S times S is not the identity. So this is just to point out that gates do not always reverse themselves. And then pi by 4, we have the T gate, which is e to the I pi by 4 and e to the minus I pi by 4. So they're just, so that's T dagger, which again is different to T T is not its own inverse. So I think we have introduced the important single qubit gates here. And before we move on to talking about multiple qubit gates and so on, I would like to introduce a different notation for looking at how we write gates. So let's call this slide Dirac notation or bracket notation for gates. And what we're going to need here is something called the outer product. So we looked at the inner product where we had the bra of a state times the ket, and with the outer product, instead we're going to have the ket times the bra. So the outer product of A and B is the ket A times the bra B, and we often kind of write this, well, yeah, you can write it either way. You can kind of bring them together and then it's kind of easier to write. So the outer product, to work out what it means, let's actually work it out explicitly for some vectors. So let's say that, let's work it out for 4 cases, 0, 0, 0, 1, 1, 0, and 1, 1. If we have 0, 0, we have 1, 0, 1, 0. This is going to be 1, 0, 0, 0. And here we're going to have 1, 0, 0, 1. That's going to be 0, 1, 0, 0. Here we're going to have 0, 1, 1, 0. Sorry, I have just done this the wrong way around. Yeah, I will just erase these because I wrote what we'd work out for the inner product, not the outer product. I need to switch the bras and kets. So we have 1, 0, 0, 1. And now you can see by multiplying each element, 1, 0, 1, 0, you can see by multiplying each element, we can create the 1, 0, 0, 0. And 1, 0, 0, 1, multiplying each element, we will find 0, 1, 0, 0. And 0, 1, 1, 0 will get our 1 being in the other corner, and 0, 1, 0, 1, we get the 1 in this corner. And what is exciting about this is that we can take a linear combination of these 4 outer products, say alpha, beta, gamma, delta, and in matrix form, we will have a matrix with 4 elements. And so we can express any matrix in terms of our bra-ket notation using these outer products. And this can be useful for doing calculations because you can express your state in terms of, you can express the operator in terms of bras and kets instead of as matrices. So you can choose whether you calculate in terms of matrices or using bras and kets. So another thing to note is that we didn't have to use just 1 second. So we didn't have to use these 4 outer products. We could have used any set of 4 outer products with which we can build up the matrices. So we could have instead used plus and minus, but in this case we would have different coefficients. So you can work out what the relationship between these primed coefficients and the ones in the 0, 1 basis are. And in this case, when we write out this matrix, we are doing it with the assumption that the basis of the matrix is the plus minus basis, not the 0, 1 basis. So you have to be careful that you know which basis your matrix is written in, and to notice that when you're converting between the matrix representation and that of outer products. So just to give an example of expressing the gates we looked at earlier in terms of outer products, the X gate was 0, 1, 1, 0. So as an outer product, that's 0, 1 plus 1, 0. And if you apply the X gate to the state 0, then we have 0, 1 plus 1, 0 applied to the state 0. We can multiply this out. And then you'll see here that this inner product becomes 0. This inner product becomes 1. And we end up with the state 0. No, that is not correct. X applied to 0, we have that 1 goes to 0, and we end up with the state 1, which is correct. X flips 0 to 1. So you can choose either method, multiplying out the matrices or using the outer product notation to do calculations, and sometimes one will be easier than the other. So I think we have explored the world of a single qubit quite a lot now, and we're ready to move on to multiple qubits. So let's create a new slide, and I'll just start by calling it multiple qubits. Now, when we have multiple qubits interacting, we have to kind of drop our block sphere picture. There isn't as nice a geometric way of looking at the state of two qubits, so we won't be thinking about that as much here. So let's think about how we can write down the state of multiple qubits. If we have a qubit in the state A and a qubit in the state B, how do we write the overall state of these two qubits? Well, we're going to introduce something called a tensor product, which is our third product of the day. We've had inner products, outer products, and now we have tensor products. So the tensor product we denote using this symbol with a circle and a cross in the middle. So the tensor product of A and B we write like this. And often we just use the shorthand of writing it all as one ket. And it's assumed that we're doing a tensor product between A and B. So we can see what a tensor product means mathematically by looking at it in terms of the vectors. So the vector A, let's say that's A1, A2. The vector B is B1, B2. And then vector A tensor vector B means that we do each element of A multiplied by all the elements of B. So we create a kind of giant vector. So we have A1 times B1 and B2, A2 times B1 and B2. And so this creates a vector with 4 entries. And we have this product of the elements. And so this vector with 4 entries describes the state of both our qubits. But most of the time when we're working with tensor products, we don't actually need to calculate this multiplication of the vectors, because we can do lots of things to apply gates to the qubits without actually needing to multiply them out. It's easier to work with this notation here. And so this is what we do when we do the tensor product of vectors. But if we want to apply different quantum gates to each of these qubits, then we also need to do a tensor product of operators. So if we do tensor product of operators, so say we have an operator A that we want to act on the ket A, and an operator B that we want to act on the ket B, then we can do that using a tensor product of A and B. So the way that this works out is that the first part of the tensor product acts on the first ket, and the second operator acts on the second ket. So this is equivalent to A acting on A, tensor product with B having acted on B. And again, we won't need to work out the tensor product of A and B as matrices explicitly very often, but I will show you what it is mathematically so that you know what it actually means to be doing this tensor product. And it's just a kind of a nice mathematical feature of quantum theory that we can use these tensor products to describe how operators act on different parts of the quantum states. So don't worry too much about where the maths comes from, or why this is a tensor product, or why we're kind of, why the mathematics is this way. So again, we kind of do each element of A multiplied by the matrix for B. And actually, I won't kind of write out the full matrix here, but you can see that you can multiply A1 by each of these elements, A3 by each of these elements, and so on, to create a 4 by 4 matrix here with products of the elements. So that's what taking the tensor product of the matrices actually means. So we can use this, for example, if we want to apply an X gate to the first qubit and a Z gate to the second, then we do tensor product of X and Z applied to 0 plus 1 over root 2. No, actually, sorry. Let's just say that's to 0, 0, 1. Then we'll apply the X to the 0, so that will turn the X into a 1. It'll flip it. And we'll apply the Z to the 1, which will bring out a phase factor of -1. So this will be our final state. And you can also, you don't have to write out these two vectors in the states in the same basis. We could have written 0 plus and done X tensor Z, in which case if you work it out, then this will flip the 0 to a 1 and it'll flip the plus to a minus. So we'll end up with the 1 minus state. So that's how we denote multiple qubits and acting individually on each qubit. But we've not actually made those qubits interact. We've just been able to do gates on them individually. So let's expand our repertoire of gates to being able to do 2-qubit gates. Just see how I'm doing for time. So 2-qubit gates. So the 2-qubit gates that I want to introduce is the C0 gate, controlled NOT gate, this is called. And this is a very extremely useful gate in quantum computing because it allows us to create entanglement between qubits. So we had Hadamard was our first gate that could create superposition from a single qubit state. The controlled NOT is our way of creating entanglement. And at this point, so something that I've not mentioned so far is quantum circuits and how we write down quantum circuits. But I think this is a useful point to introduce the notation of quantum circuits so that we can see what's going on when we're using these gates. So let's do that now. So the way that, so let me do a little kind of aside on quantum circuits. The way quantum circuits work is we have these lines that, so we start off with our qubits. So say we have, we kind of by default assume that our qubits start in the state 0, but we could also write them starting in some other state. So say 1 or psi to be very general. And then we have these things which we are lines that we call wires. And these kind of represent the qubit being in a particular state over time. And then we can apply gates to these qubits to then affect their states as they as we read along this wire. So we could apply, so for the single qubit gates, we normally write them as a box with a symbol in it. So we could apply an X gate to 0, a Hadamard gate, an S, and a T dagger, and so on. And so that's how we write single qubit gates. And then the 2-qubit gate that we're introducing now, well, let me introduce another thing that we've already seen, which is measurements. We write them using a box with this kind of meter symbol inside, which is, yeah, it's like a kind of a meter, like a dial. So that's where the symbol comes from. And that gives us a measurement outcome, which will be a classical bit. And then if we want to then use that bit later on in the circuit, for instance, we want to condition some later gates on the outcome of that bit, then we represent the output wires of that using 2 lines to show that it's classical information. And to do 2-qubit gates, they act on 2 wires, and in particular, the controlled NOT gate has these 2 parts. We have the control part, which is this black dot, and then we have this circle with a cross in to be the NOT part. So let's see what a control NOT gate means. A control NOT gate acts on 2 qubits, so we can write it as C0 or CX because the NOT can be written as an X. So if we do CX on 0, 0, so if the control NOT gate has is controlled on the first qubit and targets on the second qubit. If the first qubit is 0, then it does nothing to the second, and if the first qubit is 1, then it applies the X gate to the second and flips it to the state, to whichever state it ends up in after applying the X gate. So if we apply it to 0, 0, then it stays as it is. If we apply it to 0, 1, it also stays as it is because the control is 0. If we apply it to 1, 0, the control is 1, so it flips it to 1, 1. And if we apply it to 1, 1, then the control is 1, so it flips it to 1, 0. So that's what the control NOT does to the computational basis states. So I should mention that when we have 2 qubits, instead of just having 2 computational basis states, 0 and 1, which we had for 1 qubit, we now need 4 basis states to describe our any possible state that 2 qubits can be in. So any state that 2 qubits can be in is a linear combination of these 4 basis states. And as before, they could be in terms of plus and minus instead of 0 and 1, but they have to form a basis. So the inner products of each of the 4 kets with each other has to be 0. They have to be orthogonal. So where this gets interesting is if we start with, if we have a circuit where we start with 0, 0, we apply a Hadamard gate and then a control NOT, then let's see what happens. So we have 0, 0, then we applied a Hadamard, so we got 0 plus 1, and I'm going to ignore the normalization for now, just to make it simpler to look at. And then we apply the control NOT. Well, this state is 0, 0 plus 1, 0. So the C0 is going to leave the 0, 0 as it is. And on the 1, 0 is going to it's going to flip the second 0 to a 1. So we have 0, 0 plus 1, 1. And then we say that this state is maximally entangled because if we measure it in the Z basis, then if we get a if we measure the first qubit and we get a 0, we know the second qubit is a 0. If we measure the first and we get a 1, we know the second qubit is a 1. And what's more, we could also write this in terms of plus and minus, and it works out that it is equal to plus 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 minus minus. And so this means that if we measure it in the plus minus basis, then we also have this kind of correlation between measuring that the first qubit is plus, and then we know the second qubit is plus. And the fact that we can have these correlations in these two different bases is what makes these correlations go beyond what classical objects can have, like a pair of socks being on opposite sides of the universe. You still know that the other pair is matching it, but having these correlations in two different bases means that it goes beyond classical correlations. And this is the kind of first hint that we can do information processing beyond what's allowed classically. So given this, another kind of side note to mention here is that if we actually, how would we represent measuring in a different basis on a quantum circuit if we did want to measure in the plus and minus basis? Well, let's just rewrite our circuit. In that case, what we would do is, because kind of physically we can only measure in one basis, which we've kind of defined to be the Z basis, we have to map the plus states to 0 states and the minus states to 1 states, so that when we do our measurements in the 0-1 basis, the computational one, we'll get the same measurement statistics that we would have got if we'd been able to measure our state in the plus minus basis. So we need to apply the gate that turns plus to 0 and turns minus to 1, and that's the Hadamard gate. So if we apply Hadamard gates, then we're then measuring in the plus minus basis instead of the 0-1 basis. And this is something you can do in general. If you want to measure your qubit in any other basis, then you can change which gates you apply before the measurement to map the states you're interested in to 0 states and to 1 states. So now that we have introduced the controlled NOT gates, we can see that we can create these entangled states. And I want to draw attention to some particularly important entangled states. So these are called the Bell states. Okay, so we can create the Bell states essentially by changing what we start with in this circuit. So if we start with 0, 0, we see we get 0, 0 plus 1, 1. And we can kind of explore these 4 options of starting with 0, 1, 1, 0, or 1, 1. And what you will find is that we end up with these 4 states where we have 0, 0, minus 1, 1, 0, 1 plus 1, 0, and 0, 1 minus 1, 0. And we denote these by phi plus, phi minus, psi plus, and psi minus. And you can check that these 4 Bell states actually form an orthonormal basis. So each of them are, they're all, if we just denote a general one by phi I and phi j, then they're all orthogonal. And so each of these Bell states are what we call maximally entangled, which means that the two qubits that they represent are maximally entangled in the computational basis. And we are coming up to the end of the lecture, so I'll just mention a couple more things about entangled states. So one thing I want to mention is pure and mixed states. So we have this, let's say we have this entangled state 0, 0 plus 1, 1. And then we have these two qubits described by this overall state. Well, what if we just want to look at the state of one of these systems on its own instead of both qubits together? How can we describe the state of that qubit on its own? To understand that, we're going to need to introduce something called a density matrix. So the way this works is if our state is psi, then we can take the outer product of psi with itself, and we call this rho. And this is a matrix where we can write it out like this. So we can see that we have these terms of the matrix. And this can be written out in terms of a 4x4 matrix where we have ones in the corners. And this means that we can represent our overall state of the two qubits using this, this matrix called the density matrix instead of the ket notation, which we call the state vector. So this is an alternative way we can represent that. And what's useful about this is that we can get individual density matrices for the individual qubits to describe their states. So we do this by doing something called the partial trace. So if we call the overall state rho 1, 2, then to get rho 1, we do the trace, we denote it like this. So we do the trace, the partial trace over the second qubit of rho 1, 2. So the way that a trace works is that for a matrix, the trace is the sum of the diagonal elements. And in the bracket notation, that's going to be the sum of kind of doing the so we do the bra of each basis state and the ket of each basis state on either side of our state to extract the diagonal elements, and then we add them together to get the trace of a matrix. But if we do the partial trace, this means that we are only doing this for one of the qubits. So we can rewrite this state here as we can kind of separate out each term into the two vectors that into the two states we're interested in. So sorry, that's 1, 0, and 1, 0. And this one should have been 0, 1, tensor 0, 1. Then we have 1, 1, tensor 1, 1. And so take the trace of each of the second qubits here. So you can see that the trace of 0, 0 is going to be 1 because it just has one diagonal element, adds up to 1. So that leaves us with the first qubit. So this has trace 1, 0, 1 has trace 0, 1, 0 has trace 0, and 1, 1 has trace 1. And so we just multiply the state of the first qubit by each of those factors, and then we end up with 0, 0 plus 1, 1. So this is our density matrix for just the first qubit. So it's 1, 0, 0, 1. And what you'll find if you do the same for the second qubit, then its density matrix will also be 1, 0 plus 1, 1. And I missed out the normalizations when we were doing this multiplication. So what you'll find if you put those back in is we end up with a factor of 1/2 here. And what this is telling us is that if we look at each individual qubit on its own, it's as though it had half probability of being prepared in the 0 state and half probability of being prepared in the 1 state, but we don't know which is which. So when we measure that state, we've got a half chance of seeing 0 and a half chance of seeing 1, but it's a statistical mixture of 0 and 1 instead of being a superposition of 0 and 1. So it's different to having the state being 0 plus 1. And so if we look at each qubit individually, we have this statistical mixture of 0 and 1, and we say that these are mixed states. And that means that they don't have a definite state that we can write out using a state vector. To write it out using a state vector, we need to look at both systems together, and then we have this overall entangled state. So the individual states we have here they don't tell us whether these qubits are entangled or not. They just mean that we'll get outcomes as though we have a statistical mixture of the state 0 and states 1. And the significance of mixed states on the block sphere is that pure states are all on the surface of the sphere, whereas mixed states are, so this mixed state where we have 1/2, 0 and 1/2, 1 is right in the center of the block sphere. So every point inside the block sphere can be represented by a mixed state. So that is how pure and mixed states work. And now we will kind of put lots of the things that we've learnt today together in order to understand a quantum algorithm. And in particular, we're going to look at quantum teleportation, which is a fun algorithm to look at. Okay, so what's exciting about quantum teleportation is that it allows us to get a quantum state, an unknown quantum state, and then by doing some interactions between that state and another quantum state, which we know is entangled with a faraway quantum state that someone else has, we can make our two qubits interact, send that person some classical information, and then they can use that to reconstruct our quantum state, which was unknown, on wherever they are in the world, in the universe. So it's called quantum teleportation because we seem to be able to transport the state of some unknown quantum system from one place to another by only sending classical information from one place to another. And that's making use of the fact that our two qubits are entangled. So just to set the scene here, let's say we have two people. We have Alice and Bob. And they are trying to, let's put Bob on the other side. And Alice and Bob have these two qubits, which are entangled. And now Alice has a qubit in an unknown state, and she wants to transport that state to Bob. And let's say Alice and Bob are very far away. Maybe they met once at a conference and then started a research collaboration, but they've now both gone back to their distant places, in someone in the UK and someone in Australia or something. And they are now trying to do an experiment together, and somehow they've managed to get entangled qubits on opposite sides of the world. And then what they can do is they're allowed to phone each other, so they can send classical information over the phone, but they can't send any quantum information to each other. So how this setup works, we're going to write it as a quantum circuit. So the quantum circuit is going to involve some qubits. We've got a qubit in an unknown state, let's call that psi. And then we've got our, well, Alice and Bob's qubits that are entangled. So to entangle them, we prepare them in this Bell state using the Hadamard and C-dot gates. And then, so Alice has these and Bob has this. And then what Alice does is something called a Bell basis measurement, which essentially we reverse the, we do the C-dot then the Hadamard instead of Hadamard then C-dot, because we're essentially, what this does is it maps Bell states to computational basis states. And this turns out to give us some nice outcomes. And let's see what happens when we run through this circuit so far. So we have this general unknown state, then we have psi 0, 0 goes to, let's just write it out. We have an entangled state 0, 0 plus 1, 1, which is alpha 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 0, 0 plus beta 1, 1, 1. And then when we do the C0, then that's alpha 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 1, 0 plus beta 1, 0, 1. And then we do the Hadamard on the first qubit. And writing this out, we get 8 terms because we've turned our 0 to a plus and we've turned our 1 to a minus. And you can work through this yourself to check that all the maths is correct. And it should be a 1. And what you can find is that we can simplify this state to, you can kind of extract 0, 0, and then we have alpha 0. So if we look at the other state with 0, 0 at the start, we have alpha 0 plus beta 1. And you can do this for all our states. So if you do this algebra plus 1, 1, so just going off the screen a bit now. And what you can notice is that each of these states that qubit B that correspond to these 4 states, each of the states that qubit B can be in are some manipulation of the state psi. So this is just the state psi. This is Z applied to psi. This is X applied to psi. And this is X and Z applied to psi. And so if Alice measures these qubits and then gets, she sees if she gets 0, 0, she'll project into this state, and Bob will definitely be in the state where he has psi. If she has 1, 0, then Bob will be projected into the state Z psi, and so on. So Bob just needs to apply gates to his qubit, conditional on the outcomes that Alice got. So she can call him up on the phone and say, Bob, I got 1, 0. And so that means that you need to apply a Z gate to your qubit to get the state psi back. And so we can write this by writing controlled gates on our circuit, controlled on the classical outcomes. So we could do a controlled X gate on the second outcome and controlled Z gate. So they'll be applied if it's 1 and not applied if it's 0. And you can check that this corresponds to these 4 outcomes. And after applying those gates, Bob will have psi. And so even if Bob's qubit at this point of the circuit was made to be very far away from Alice's qubit, they have managed to teleport the state psi from Alice to Bob just by sending about whether to apply X and Z. So, and just to summarize what we have been through today, we have looked at these building blocks of quantum, looking at the fundamental aspects of linear algebra and how to manipulate single qubits, and then how to manipulate multiple qubits, some of the gates that are important there, what pure and mixed states mean, and also quantum teleportation. And I've just noticed here, there was one thing we didn't get around to mentioning, universality. So the point of that is that we can build up any quantum circuit we like. So we can implement any gates we like, just using a small set of gates. So using single qubit gates and control not gates, we can actually build up any gate that you could think of, say 3 qubit gates and so on, to arbitrary accuracy. So we can always use combinations of this, what we call a universal gate set, to approximate any gate we want. So that means that we can use these elementary gates to perform any quantum circuit we want. So I hope you found that interesting and useful as an introduction to the building blocks of quantum information. There's, I think, essentially all these ideas are covered in the Qiskit textbook, so that's a good place to look if you want to go through things more slowly and have some interactive ways to explore these things with Qiskit. So thank you for listening, and I'll see you in the next quantum lecture for the summer school. Okay, bye.